In today's episode, we're going to talk about how malware authors evolve from using a simple packers designed to compress executable files to much more comprehensive schemas of abusing multiple layers of packing or abusing advanced protectors, making it much harder to actually detect known malware using signatures or even using heuristics, because the code of the malware would be protected by more advanced protector technologies or multiple layers of primitive packers or both together. Hope you're going to enjoy it. Let's discuss it in more details. If you remember from our previous episode about 2000 to 2005, malware authors were already using packers, executable files packers, to either compress their malware or abusing the packers to actually make it harder to create a signature for the file. The way packers would work, they would compress the original file, add extra code of unpacker, and of course it's still going to be an executable file. But that result compressed file would be much smaller than original file. That's how the standard packers would work. For some time between 2000 and 2005, malware authors would abuse them and use them to pack the malware. But antivirus vendors would find the easy way to implement statically the algorithm which would convert the packed file into unpacked very easily. So the way malware authors start to abusing it, so let's say that was, I don't know, UPX, right? Even though UPX works slightly differently, let's say it is UPX. What they would do, instead of just having one layer of packing, they would take that packed file and pack it again with, I don't know, let's say ASPack. And then they would do it again. And at some point, because the data is already as compressed as possible, there would be almost any benefit of compressing, so the file would be, they even try to compress it, but actually file would start growing in size because they would be adding these new layers of unpacking. And let's say in this case they would call it MU, right? That's another known packet. And they would continue farther and farther and farther and farther, and maybe do it 10 to 12 times, and would end up with the final file, which they now can take, and that's a final compressed malware. And of course, all these different packers they use, even though they're all known, but they can mix and match them in a different combination. So, instead of UPX at first, they can actually use SPack next time, and use UPX here, and maybe use SPack again, right? And just do it over and over and over again for as many as 10, 12, even sometimes 15 times, and having that final result. So the problem with that for anti-malware vendors would be that, first of all, to unpack such malware, they would need to support every single packer which we used in this chain. And second of all, it actually becomes pretty cumbersome to go backward so many layers, because unpacking by itself is CPU intense and memory intense procedure, even with one layer. But doing it 15 times and do it in a reasonable time, of course, let's say that if the file's packed like this, it might take a significant time, CPU time, for anti-malware vendor to unpack it. And that became a problem for many of the engines at first, because they were actually not able to first support all the variety of available packers, but also sometimes the way the unpacking happens, file might end up being slightly corrupted, or the tables are not the place they were expected to be, and it just became kind of a very cumbersome operation to unroll all these layers of packing. So that was the first strategy which malware authors would use to make it much harder for antivirus engines to simply unpack known packers. However, at this point, they still would use those simple packers which were not designed to actually hide the code. Instead, they were just designed to compress, but just by utilizing many of them in a row, they reach certain level of protection of the malicious code, specifically against automated antivirus engines, which could not spend minutes to analyze every file. Of course, they were limited how many layers they could unpack at one go. Another strategy to make it much more complicated for antivirus engines to analyze malicious code was using advanced protectors were historically used for actually legitimate purposes. They were used to prevent reverse engineering and cracking of legitimate software. Very popular protectors were, for example, for game developers who didn't want people to cheat in their games. For example, if it's an online game, they want to prevent people from reverse engineering the algorithm and cheat the game. And actually, those type of techniques are still used even nowadays to prevent cheating. Back in the day, between 2005 to 2010, most of the software were still working offline. It wasn't like a SaaS type of software where key would be checked against online server, and it would be assumed that software only works if it's online. Most of the software were still offline, they were installed offline. That software would need to be activated with some sort of key, right? And the one way to prevent reverse engineers easily reverse engineer algorithm for the key verification would be to use that protectors who make it very, very difficult to reverse engineer file. And specifically, the way that the protectors would do it, first of all, the protectors would embed anti-debugging. So every time you would attach debugger to a file protected by a protector, there would be some functionality inside which tries to different ways detect the debugger, either through some legitimate flags or through some sort of side channels, for example, by throwing hundreds or thousands of exceptions, and if there is debugger attached, the debugger would change the execution flow of the software itself. So they would use the under-debugging to make it really hard to reverse engineer. They would also make it really hard to statically unpack the file, and the reason why is because they would actually using encryption of the code and the content of the file. They wouldn't just compress it, they would encrypt it, and encryption wouldn't be just simple like one function off. They might, for example, encrypt just strings for each function or data section. So the encryption might be very complex and multi-layers. It's pretty much it would be impossible, but it would be very difficult and would be designed that way to automatically decrypt things. More sophisticated ones would use kernel drivers. When the program encrypted the protected by protectors would run, it would actually drop the driver as a file. And then it would start communicate. So let's say it's a kernel, that's a userland in Windows operating system. That's our original file. So it will load the driver, and then it would start communicate with that driver back and forth, and it could either request some extra information about the system or some entropy information or whatever else it can request from a driver. The point is, without the driver, it will not continue execution. Meaning the only way to really decrypt it, like the driver, for example, can have a key inside, and only way to decrypt it would be actually using the driver. That makes it pretty much impossible to easily decrypt such protectors. Statically, even dynamically, it becomes a real problem. There would be even more complicated approach is virtual machines. What the protectors would do, they would analyze the code of original file, right? That would be the code. And that they could find certain pieces of this code, certain function, and they can convert it into their own P code. So it's not x86 code anymore. It's actually P code, which then interpreted, and they would add that layer of the Packer VM, right, which then interprets that P code and executes how it should execute. So let's see a hypothetical example. How would advanced protector work if it has a binary to protect? So first, it can analyze the binary and understand where the code is, where the data is, where the import table is, and find all the references between the code and import table, for example, and the code and the strings in the data section, right? So analysis happens. Now, what it can do, and the goal of the protector is not really to compress the executable, it's to make it hard to reverse engineer. So the protected executable may actually be much bigger, and when it copies the original executable, as I said, it analyzes it. So it's not necessarily copying the original code and data section, but it might modify them. For example, as I say, it can encrypt the strings or data section and add extra decryptor layer, which would execute before the original code executes and decrypt those strings. It can also analyze import tape, find all the places where the imports are called, the system APIs are called, and it would replace it with the calls to the same location to its own code, where this would actually have an import redirector, and based on the return address of that call, it would know the location, right? So here there would be a table of what actual import it needs to call, and that would be import table. So it would translate and redirect those calls through its own table to call a proper import. So when you open it in disassembler, instead of seeing clear APIs which application is using, you would see just a call to the same location, which might be very obfuscated and very unclear. And that import table I mentioned here, that might actually be built dynamically, so you would not even see it again if you try to reverse engineer the file. You can also have a kernel driver and so on. So it actually might be much more bigger executable file than an original one, and much more complicated and very, very difficult to unpack and analyze. Now imagine you're combining these two techniques together. You have an executable file and you first protect it, make it very hard to reverse engineer. For example, you use Armadillo protector and it becomes very, very hard to analyze it, and then you compress it to make it smaller. And then if you want to, you can do another protector later, and so on, right? So you can actually have multiple layers of compression and packing, and from original executable you can really get to the state where it's very, very hard in a reasonable amount of time with a reasonable computation resources to get original state of the executable. And that became actually a big problem for antivirus engines. A lot of them would try to implement some static unpacking, but static unpacking would not work very well here at all. So that's how the new technology in anti-malware engines, new unpacking technology would be developed as well. And we're going to talk about this later.